Okay, so this is for chapter one or from the workbook. There's a lot of different definitions that you need to know, which are all in the class notes. So this is actually the class notes for that chapter. And not because I'm going to ask you to define it per se, but I'm going to ask you to, for example, to tell me the outcomes for that experiment or the sample space for that experiment, or to name an event, to find the empirical experimental probability, or to find the theoretical probability, or, are these outcomes equally likely? See, so you need to be able to know these definitions. So again, this is part of your class notes, and you're welcome to stop the video and then look at them and write the definitions, or you're welcome to look at the class notes. So first of all, when you're finding probability, right? That being said, if it's experimental or theoretical, you're always going to have the probability of that event happening over the total sample space elements, okay? So if you toss a die, right? A die has 6 sides, a 6-sided die. So the probability of getting the number 2 is 1 out of 6. So 1 is the part, they're getting a 2, right? So there's only 1 2 in the die, and 6 will be the total number of faces, right? The total number of numbers in the die. So and impossible probability and certain probability. So you need to come up actually with an impossible probability and a certain probability, an event for the homework and for your test as well. So what is an impossible probability? Impossible probability, yes, is that the probability is equal to 0. So for example, and I always tell my students, you make it simple as possible. Don't make complicated. If you have a box of red markers, what is the probability of pulling a blue marker? 0, because the box is full of red markers, right? So that is an impossible probability. A certain probability, which is equal to 1, right? That is 100% that happening. If you have a box of red markers, what is the probability of getting out a red marker? 100%, 1. So that's a certain probability, and then the previous one was an impossible probability. So you need to give examples on the homework and on the test of an impossible and a certain. Like I said, don't make it complicated. Make it as easy as possible. And yes, just to clarify, because a lot of students say that, oh, what is the probability of getting heads? That is not a certain probability, okay? So, or getting a number 1 through 6. You need to be able to be very specific, so you are 100% that always going to happen to be a certain probability, okay? Law of large numbers, which we're going to be related to the theoretical probability, is that if you repeat an experiment millions and millions and millions of times, it's going to tend to a specific number. Okay, so for example, maybe when you're doing the first activity that you have in your workbook is doing 3 different type of events, right? Tossing 2 coins, tossing 2 die, tossing a spinner that has two sides. So 2 spinners. So again, all of those are going to be just a limited number of times that you can do that experiment. But if you repeat those experiments hundreds of times and thousands of times, you are going to see that maybe when you toss the coin, you did not win and you needed to match, like get face or heads, and you did not win. The other one win, the one that they didn't have the same thing. That doesn't mean that it is not 1/2 the probability. So of tossing face or tossing head. So yes, so things need to be seen as in the long run what will happen. So I know in the class notes you have exactly the same thing, but you cannot move this, and I can't. So I'm just going to go quickly over it so you have the answers, so you know if you're doing it right or wrong. So suppose an experiment consists of drawing 1 slip of paper from a jar containing 12 slips of paper, each with a different month of the year written on it. Find the following. So the sample space, remember the sample space is the collection of all the outcomes. So if we have 12 slips of paper, and in each one you have a different month of the year, that means that one of the outcomes, when you pull your hand in out of the jar, you're going to have either January or February or March or April, right? Any of those months of the year. And we write, these are sets, right? It's a sample space, they're sets. So if you remember from 1350, right, about sets, we write the sets with capital letter equal to, and then the little braces, and we separate the data with comma, okay? Each member with a comma. Then it says the event, and then see how you create, because you're going to have to create events, right? Also as well in your homework and on your test. So you need to, the event, in the experiment in this case is just having the month of the year in a jar, right? So, and then from there you create specific events, and you're going to see we have several ones in here. It says event A consists of the outcomes having the month that begins with J. See, that's very specific. So even though you have 12 pieces of paper in a jar, right? And there's 12 possible outcomes. You're only looking specifically for the month that start with J. So those will be January, June, and July, right? Event B, consisting of the outcomes having the name of a month that has exactly 4 letters. So again, which are the months with exactly 4 letters? June and July. The event C, consisting of the outcomes having the month that begins with M or N. And the reason I circle or is so if you recall in the sets when you did it in 1350, or means union, right? So that means you're going to consider all the months that start with M, and you're going to add to that all the months that start with N, right? So we're going to have the collection of March, May, and November. Then we have, in this example, you have the numbers 1 through 25 in the sample space. And you're going to choose at random. That means that they have equally likely chance to come out. You're going to choose at random one number, right? So again, you have a total of 25 numbers. So that means that the number of elements, and just to recall, remember that this notation, that N means number of elements, and then the letter inside is the letter of the set. So event A, so how many elements does event A has? Well, I don't know. Event A, you need to find the number of even numbers drawn. So you need to find all the even numbers from 1 to 25, right? So the first thing you need to do, if I can move this, is to label what A is. A will be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, right? So that means that the number of elements on A is 12. Okay, so that's what we will put up here. And again, how many elements are in the sample space? Because S is always for the sample space. So we got 25, right? So then that will be 12 out of 25, which is your probability of getting an even number drawn. Okay. Even B is that the number is less than 10 and, let me circle that and greater than 20. So again, and means that they both need to happen. It's an intersection. So can a number be less than 10 and at the same time be greater than 20? No, see, this is an example of an impossible probability. See, this is called empty set. I don't know if you guys remember that, empty set. And so that means the probability is 0. This is an impossible probability, okay? Because there is no way for a number to be less than 10 and at the same time be greater than 20, okay? If it was or, what's a different story, but this is and. And then look at the next one. The next one says an event C is that a number that is less than 26 is drawn. Well, all the numbers are less than 26. So this is a certain probability, right? Because they all are going to be including because they're all less than 26. Event D is that a number is prime, okay? So again, you're going to list all the prime numbers, 2, 3, 5, 7, 11, 13, 17, 19, 23, all the prime numbers between 1 and 25. And so you see that the number of elements of D is 9. So that will be 9 over 25. And then you have even E, that the number that a number is both even and a prime is drawn. So what is D? Only even and prime number is 2. And how many 2's do we have in the list? Just 1. So that means the probability is 1 over 25. Okay. So as you see, you are going to have always the probabilities once you work through the activities in your workbook, those first activities with the tossing of the dice, tossing of the coins and the spinners. Once you go through those, you're going to see that always the probability is going to be between 0 and 1. You also have some other activities, which is what is in the bag, which is also, you're also going to go through different type of probabilities. You can also play with that on those. And then we define again the impossible and the certain probabilities. Okay. The other thing you need to be familiarized with, and again, I would suggest write it down, take a picture, is the cards, because you do have deck of cards on the homework. You do have deck of cards, I think on the homework, but if not on the test, you do have certainly deck of cards. So in a deck of card, a regular deck of card, we're not playing Old Maid here, is going to have 4 suits. And if you see the suits, these are the suits right here. So we have the heart, which is red, the diamond, which is red, spades, which is black. This is the spades. And then clubs, which is also black. So as you see, half of them are black and half of them are red. There is a total of 52 cards. And each suit, as you can see, has 13 cards, okay? We don't have 1, we just have A. And then after 10, we got what we call face cards. This doesn't have faces, but this one do. Face cards, see right here? And it's jack, queens, and kings that are called face cards, okay? So each suit has 3 face cards, and there's a total of 13 cards in each suit. And obviously, as you see, half of them are red, so that means 26 are red and 26 are black, for a total of 52. Okay, so remember those numbers. So it says we draw a card at random from an ordinary deck of playing cards. What is the probability that the card is an ace? So remember, we got 4 suits, and each suit has an ace. So that means we got 4 out of 52, which you're gonna have to reduce to 113. Yes, I take points off if you don't reduce it on the homework. I take points off if you don't reduce it on the test. Okay. The card that is an ace or a queen. Remember the ors, right? Or means union. Okay. So you're collecting all the aces and all the queens. So we know we have 4 aces and 4 queens. So we have a total of 8 cards, right? And then out of 52, because that's the total, and we reduce it to 2 13s. That the card is red. We already know that a red queen, sorry, that the card is a red queen. So we already know we have 2 suits, they're red. So that means we're going to have 2 queens that are red. And that is reduced to 126. And the card that is a black face card. So remember, we have 3 face cards on each suit, but we're only looking at the ones that are black. So spades and clubs. So that means that we got 3 clubs that are face cards and 3 spades that are face cards. So we got a total of 6 black face cards, which reduce it to 326. Okay. Now, we are also going to see mutually exclusive and non-mutually exclusive. So before, in those problems that we saw with the numbers 1 to 25, right, we saw those that were prime and even. So prime numbers and the even numbers have something in common. So that means that not necessarily is mutually exclusive. They share some things. Okay. So mutually exclusive is they don't have any elements in common. So this is a sample space that goes from 0 to 9, right? Has 10 elements. A contains 0 through 4, and B contains 5 and 7. See, A and B are mutually exclusive. They don't have anything in common, okay? So when that case happens, right, and you want to find the probability of A and the probability of B, which is with the word or, okay, which is a union, like I said before, you're going to find the probability of A, which in our case, right, if we use this case right here, A has 1, 2, 3, 4, 5. So this will be 5 out of 10. And B has 2 out of 10. So that means that this probability is 7 out of 10. I'm sorry, it's not writing right now. Let's see. 7 out of 10. Okay. So again, probability of the union of the events such that any 2 are mutually exclusive is the sum of the probability of those events. Okay. Again, they don't share anything for the mutually exclusive. For the non-mutually exclusive, right, you're going to see here you have 3, 7, 21, 18, 2, 14, 11, and 9. So even though none of the numbers repeat, you take a look at the events that we're looking at. So event E is that you spin an even number out of this right here. Now let's take a look. We have 1, 2, 3, 4, 5, 6, 7, 8. We have a total of 8 equal pieces in the spinner. So my sample space is 8. And then for even, you will have 14, 2, and 18. So we got 3 of them that are even. Then it says, let event T be spinning a multiple of 7. So of course we got 7, we got 14, and we got 21. Now, what do you notice? Are these events, E and T, mutually exclusive? No, because they both share 14. So when you're trying to find the probability of the union, you are going to find the probability of event E. You're also going to add the probability of event T, but then you're going to subtract what they have in common. And since they only have in common 1 element, then when you're going to subtract that 1 element, the probability of that 1 element. So since you only have 114, it will be 1/8, 1 out of the 8. So we got 3 out of the 8 for the even. We got 3 out of 8 for the multiples of 7, but then we need to subtract whatever they have in common, which is that 114, and that would leave you with 5/8. And it makes sense, right? Because if you were going to add them all once, you don't count it twice. So we will add the 2, that's 1, the 14, that's 2, the 7, that's 3, the 21, that's 4, and the 18, that's 5. See, 5 over 18. So if you were to pick one individually without repeating. Okay. Now we also have some what we call complementary events, and this is important, right? Because when they ask to find the complement and how to label. So 2 mutually exclusive events, remember they don't share anything, whose union is the sample space are complementary. So if you say, for example, consider the events A being 2 and 4. of tossing a 2 or a 4 using a standard die. Remember that in the standard die, we have 6 numbers, 6 faces, 6 numbers. So we would say that the complement of A, which we write with the little bar on top, is everything that is not in A, but is part of the sample space. So we don't have 2 or 4, right? So we already have 2 or 4, so we're left with 1, 3, 5, and 6. And if you see, when you add the independent probability, the probability of event A plus the probability of the complement of event A, you are going to get equals to 1, see? And with knowing that, you can solve this equation for any of it. You can solve it if you have the complement. You can solve for finding P of A. If you have the P of A, you can solve it to find the complement. So either one, you can use this equation to be able to find whatever you're missing for the complements. So let's take a quick look here. It says a golf bag contains 2 red tees, 4 blue tees, and 5 white tees. What is the probability of the event R that a tee drawn at random is red? So again, how many reds do we have? We have 2 reds. But what else we also need to find probability? The total number of elements in the sample space, right? So we are going to do N of S is going to be what? 2 plus 4 is 6, and 6 plus 5 is 11. So you have a total of 11 tees in the bag, right? So now that we know the total, then now we can find the probability of the red. So we got 2 red, so that's going to be 2 out of the 11, okay? Now, not red or not R, right? They're talking about the complement. So there's different ways you can do it, but the whole point that they're giving you not R is so you can go ahead, if you know there's a total of 11 in the bag, and you know that how many are red, and you want to find how many are not red, you're just going to subtract 1 minus 2 over 11, which is 9/11, right? So remember that 1, when you're doing fractions, it turns into an 11 over 11, and then you have 11 minus 2, 11, and that's how it gives you the 9/11. And then it says, what is the probability of the event that a T drawn at random is either red or blue? So again, it's the union. So since a T cannot be red and blue at the same time, they are considered mutually exclusive events. So that means you're going to find the probability of red, which we already know is 2/11, plus the probability of blue, which we got 4 blue T's, right? So that's 4/11. So you get that the probability of red or blue is 6/11. Okay, so again, we add 2 more or 3 more to that list. We know that when you have non-mutually exclusive, you got to subtract whatever they have in common. When they are mutually exclusive, we just add the independent probability of those events. And then we have the complement. We can find it by subtracting the probability of that event from 1. Okay. Now, from here, this is all part of your workbook. So this is like page 3, 4, 5, and 6, and 7. So basically, you can flip the coin using the link, roll a die, or do the spinners, right? And again, all this is going to change. Now, obviously, you will have different answers as you go, but usually they're around the same. People get 10 and 10 or 7 and 13. So depending on the players, right? Depending on how many you get it. But what is not going to change is the outcomes, is the sample space, is the probability of event 1 or probability of event 2. Those are not going to change. Obviously, the only thing you need to do here is reduce it, okay? When you're tossing a die, as you see, the die, you needed to add the faces of the die, right? And then player 1 got a point if you get an even sum, and player 2 got a point if you get an odd sum. So again, player 1, if it's 2, 4, 6, 8, 10, or 12, got a point. And then player 2, if you got 3, 5, 7, 9, and 11, got the point. You're going to say, Ms. Escobar, but this doesn't seem fair, because see, even you have 1, 2, 3, 4, 5, 6 numbers, and then odd, you only have 5. Well, you're not looking at the number per se. You're looking at the number of sums that provide you a 2 or a 5 or a 10 or a 7. Okay, and for that, if we take a look at the outcomes that you needed to fill out, right? That you had the little table. These are the faces of one die, and these are the faces of the other die. And then if you add them, see, there's only one way to get a 2, and one way to get a 12, but there are 6 ways to get a 7. See? So you have more chances to get a 7, which is an odd number, than to get any of the even numbers, okay? 6, you got 5 ways. 8, you got 5 ways. 9, you got 4 ways, right? And when you start adding them, see, because this will be the sample space right here. right? The collection of all 36 outcomes. And then you can write it and you can even list it like this, see? Or what I actually did is that I wrote it down as a probability. So there's only 1, 2, that's 1 out of 36. There are 6 sevens, so there's 6 out of 36. And when you're writing these probability as a collection of them, just leave them with a common denominator. Once you are going to specific answers, then you can reduce them, okay? So for now, so you'll be able to add them all up, because when you add all of these, you need to get 36. If you get more than 36, then that doesn't work, okay? Or less than 36. And then here you can see by counting all the evens, right? You got a total of 18 even numbers, and you got a total of 18 even odd sums. So that's why, see, they're both equals to 1/2. And then you got the spinner, right? Again, all these results vary. They're supposed to be, you have the equally likely chance to win, lose, or tie. So, and as you see here, you have, there's just like the coins, right? Just like the coins, you are going to get A, B, B, or A, B, or B, A, right? So you're going to get the same three, like heads, 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 tails, tails, heads, tails, tails, right? It's kind of the same type of outcomes that you get when you have the spinner with only 2 faces. So as you see, the sample space has a total of 4 elements. The colors matches, that means AA and BB has 2 elements. The colors do not match, that's AB or BA, and that's also 2 elements. So as you see, once you reduce, you're going to have the same 1/2. And then the other, let me go here. Hold on. Yeah, I finished that one. And then the other one is that you have on let's see here. On page 8 on your workbook, right? It says you have a bag, and in that bag you have 5 blues, 3 yellows, and 2 greens, right? So I did the bag. So we got a total of 10. So we needed to find the theoretical probability, right? So as you go through, right, we have a total of 10. So the probability of blue will be 5 out of 10, which is 1/2. Probability of green, it will be 2 out of 10, which is 1/5. There's no red, right? So on that list, because that activity on page 8, it asks you about red. There's no red, so that will be 0. Yellow, you got 3. And then the probability of blue or yellow, again, since they're mutually exclusive, that means you can add the probability of blue, which is 5/10, with the probability of yellow, which is 3/10, and then you get a total of 8/10, which you can reduce to 4/5. And then we have the complements, the probability of not yellow. That means they're talking about the blue and green. So, but what do we do? We can subtract 1 from, we subtract the probability of yellow from 1. Yellow is 3/10, so that will be 1 minus 3/10, which is 7/10. And the probability of not green, again, green is 2/10. So we're going to do 1 minus 2/10, which is 8/10, which is reduced to 1/5. And then you have other activities in there, because it says to locate it on a number line and say if it's likely, no chance, right? You have 0, 0.25, 0.5, 0.75, and 1. So what I did is that I went ahead, you have all the little tags. And what I did is that I found those tags first. And let me see here. See, so in between 0 and 0.25, I divide 0.25 by 2, and that gives me 1.25. So, and then you're going to increase whatever tags you have by 1.25. So if you take this and add 0.125, you get 0.375. If you take 3.75 and 1.25, you get 0.5, and so on. See, until you get to 1. And then this will give you a better option, right? To where would these numbers be, right? So again, so if you have, I think this is for, that you have to classify them. I think you have to do for red, there will be 0, and then you have, let me see, green is 1/5 or 2/10. So it will be around here. And hold on. Okay, so then they ask you in this activity, they ask you to classify as no chance, nearly impossible, some chance, and even chance, likely, nearly likely, or certain. So no chance basically is 0. Nearly impossible is between 0 and 0.25. If this will write, let me undo, hold on. Anything in between that. Some chance is in between 0.25 and 0.5. So it lies in between there. An even chance, obviously, is just exactly 0.5. Likely is between 0.5 and 0.75. Nearly certain, obviously, is between 0.75 and 0.75 and 1. And then obviously certain is 1, right? So these are the periods. So 0, no chance. In between is nearly impossible. Between these two is some chance. This exactly is even chance. Between these two is likely. And then between these two is certain, nearly certain. And then obviously here it will be certain. So those are the different classifications. And according to the probabilities, right? So that's what you want to, they ask you first to graph it so you can see it. And then you can classify them into even chance. And then this is nearly impossible for the green. And then obviously it's red, there's no red, so there's no chance because the probability is 0. And then some chance for the yellow. And this is or. The thing in my notes there says off, but they fixed that in your workbook. So or, so that means that it's nearly certain because it's 4/8, right? And then a yellow, not yellow, sorry, is a likely. So this is it's in between, not yellow. Let me see, for 7/10, right? So okay, so the next thing that they have there is to state how many greens to the bag, which we had only 2, right? We only had 2 greens. How many additional greens do I need to add so we get a probability of greens as 1/2? So for that, it's recommended that you look into a table, right? Do a table and see, add 1 by 1 and see how many you need to be able to reach a probability of 1/2 or 0.5. But you need to be aware of the total of greens and the total of squares inside the bag, and then the probability as we progress. So we had 2. So if we add 1, that would be 3 greens for a total of 11 because we originally had 10, and that will give you a probability of 27.27 repeating. If you add 2, you're going to have 4 greens for a total of 12, which is give you 0.33. So it's increasing, but it's not 1/2. If you add 3, you're going to have a total of 5 greens, a total of 13 total squares, 0.38, 4, 6 greens, 14 total, 0.42, getting closer. 5, you got a total of 7 greens for a total of 15 total, and then that's 0.46. And we don't want to round, we want to have exactly 1/2. And then you see that when we reach 6, when you add 6 additional to the bag, you will have a total of 8 greens, which is and a total of squares of 16, and 8 over 16 is 0.5. So you see that you need to add 6 more greens, so you have a probability of 1/2. Okay. Then this other activity is a simulation. Like if you put inside and then you actually do the experiment, you do it 30 times. You want to see if you get the same probabilities that you will get as a theoretical probability, right? Because these are theoretical probabilities right here. And you wanted to find if we do actually the experimental, how close would it be? And of course, all this may change because these are experimental probabilities. So it's all going to depend on yours. Then this other activity, it works if you have somebody else in your home give you a bag with 8 total, but you don't know which colors. And then you repeat the experiment, but you're going to do it 40 times. And then you record it. And then, of course, from there, we can actually predict the number without looking. We can predict the number of each one in the group, in each one of the categories, just by doing some algebra, basically. And these are just some of my data for my students. But basically, you set up a proportion. And let me see if did I wrote it down in here? I don't think I did. But you set up a proportion and um, to be able to figure it out how many in each group. So you would type, for example, you would type greens and then, or green, and then say, for example, let's say we were using this first group, right? Their data, 7, 15, 18, and 40, right? So if you got 7, right? So, and it's a total of, and they appear 7 times. So we're going to do 7, and they did it, I think, 40 times. Yes, this is 40. So 7 divided by 40 is going to be equal to x out of 8 because it had a total of 8 squares inside. That much we know, right? And then once you solve with proportions, basically, in other words, you're going to have 7 times 8, and then that is going to be divided by 40. Actually, put in a parentheses because I don't want to do divided by 40, and that's going to be equal to x. And then you're going to get what? We're going to get 56. Do it right here. 56 divided by 40. that's going to be 1.4. So I don't know, we can say there is around 1 green in the bag according to these people, right? And then we repeat the same thing for all the other ones. So let me see. Let me copy all of this. Okay, let me copy. And we're going to do the same thing for blue. And then the goal for this, let's see, they have how many blue? They have 15 blue. 15 out of 40 equals to x over 8. And then we're going to do 15 times 8 divided by 40. You're going to get 3. So definitely there were 3 blues in that bag that was created at random and you did not see. So the person doing it did not see it. And then the last one, they're yellow. So we're going to put here yellow. And then yellow, they got 18. So this is going to be 18 out of 40 equals to x over 8. And then we're going to do 18 times 8 divided by 40. You're going to get 3.6. So you can approximate, again, there was a total of 4 in the bag. So we can say, okay, there's 4 yellow, 3 blue, that's 7, and then 1 green. So you can be closer to the answer or not, right? Depending on what they did originally. But this is a way that you can make a prediction. So a good prediction about how to work the problem. So in this one, we have different tree diagrams, right? So in the tree diagrams, it's another way to display probability. So in this spinner, you see it's divided into 3 equal pieces, and the colors are blue, red, and yellow, right? So if they say you're going to spin the spinner twice, right? Just similar to what you did in the first activity, but the first activity only had 2 sides, A and B, but you did have 2 spinners. So we were going to record what happens in the first spinner, what happened on the second spinner, right? Kind of similar. We're going to see what happens in the first spin and then on the second spin. But what are the possible outcomes? The possible outcomes is going to be either you get blue or you get green, yellow, or you get red. Those are the outcomes. And since they're divided into 3 equal pieces, that means that they're all going to have 1/3 of the probability of coming out. And since they are independent events, so the spinning the first time has nothing to do with spinning the second time, so they're all going to have the same probability. And then when you're finding probability of those outcomes, basically we walk through the branches. That's what they call it, 3 diagrams. So the probability of blue and then the probability of blue. So that's outcome is blue blue, probability of blue and then red, that's blue red, probability of blue and then yellow, that's blue yellow, right? Red blue, red red, red yellow, yellow blue, yellow red, yellow yellow, right? So those are the outcomes, all the outcomes, which is a sample space. And that's the sample space, and the probability of each outcome, since they're all independent and they all have equally likely chance to come out, that means that you're going to see that any branch that you go through, right, 1/3, 1/3, 1/3, 1/3, they're all going to be 1/3 times 1/3, which is 1/9. So they all have equally likely probability of 1/9. And you can do that in a tree diagram or in a matrix. See right here, this is a matrix. So you got blue, 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 yellow, blue, red, yellow, blue, yellow, 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 red, red, blue, red, yellow, red, red, right? So same story. And that's what the second activity, rock, paper, scissors, you can use. And there is, if you don't have with anybody to play with, there is a rock, paper, scissors website that I'm going to give you in a few minutes when we get to that activity. So here it says, suppose that we have toss a fair coin 3 times. See, this is very similar to the one on your homework because you toss 3 coins and record the results. Find each of the following. What is the sample space? So see right here, you have the answer for that homework problem because you toss it 3 times, okay? An event A of tossing 2 heads and 1 tail. So how many have 2 heads and 1 tail, right? So you have 2 heads and 1 tail here, 2 heads and 1 tail here, 2 heads and 1 tail here, right? So those 3 are 2 heads and 1 tail. And that's what you're going to write in the set. Then we have event B is tossing no tails. So the only one that has no tails is heads, 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 right? And then event C is tossing a head on the last toss. So see how specific that is? So this toss ahead in the last toss, this toss ahead in the last toss, this toss ahead in the last toss, and this one toss ahead in the last toss. So there are 4 different ones that toss ahead in the last toss, okay? So you see here, you have different events out of just tossing 3 dice. I mean, 3 coins. And then this is just like the one we did, you have in your first activity, right? Because they're also looking into the sum of the dice. The only difference is that their table just keep the recording of the first die and the second die. But we are doing sums, right? Just like they did here, they did the sums. And they wanted to know what was the probability of having a sum of 7 or 11. So see, a sum of 7 or 11. So basically they just added, sum of 7 is 636. Sum of 11 is 236. So when you add those two, because they're independent, you're going to get a total of what? 2 plus 6, that's 836, right? So that's what we had down here, because they're independent events, mutually exclusive. Okay. Then you says, as a fair pair of dice is rolled, let E be the event of rolling a sum that is an even number, and F, the event F, of rolling a sum that is a prime number. See what I was mentioning earlier? So, and you want to find the probability of the sum or the prime, so the union. So the union is going to include all the even numbers, 2, 4, 6, 8, 10, 12, and all the prime numbers, which is already including 2, and then we have 3, 5, 7, 11, right? So we are going to have to, there's different ways that you can do this. One way is find the probability of each one, which you have it down here, and then just add it, right? So we found the probability of 2, of 4, of 6, of 8, of 10, of 12, and then of 3, of 5, of 7, and of 11. Okay, it's not writing. Okay. So you can add all of those, or what can you do? The only number not included is 9. So you can subtract from 1, which is 36 over 36, 36, and then you can get the result, right? But so there are different ways to do the same problem. In this first one, I added all of those independently, right? And then you see that you get 32, 36. Or, again, you can use the non-mutually exclusive formula. So you add the probability of even, the probability of prime, and then subtract what they have in common, because they have in common 2. Or, like I was saying, you can find the complement of the probability of 9, and that will give you the same thing. So you see there's 3 ways, actually, 3 ways to do this problem. And they're all correct, right? So in the test and in the homework, you can come up with, use whichever one of the 3. Then you're going to see that, just like in your homework, you're also going to have it on your test. When you have, for example, when you have multiple of one color, just like we had that previous activity, right? You had 5 blues, 3 greens, and 2 yellows, or something like that, right? So instead of having to draw branches, because you are going to have to do a tree diagram on the homework, and you're going to have to do a tree diagram on your test. So instead of doing branches, like if you have 5 blue, you're not going to draw 5 blue branches. You're just going to collect them and then just say, okay, there's only 2 possibility of colors in this case. It's either black or white. So we have 1/3 or 2/3. And then the second drawing. Now, it is going to be very important that you read what are they doing once they take the first one out. In this specific case, they are replacing it. So once they look, they're going to put it back, okay? So if you're always going to put it back, that means you're always going to have the same total number of whatever units you're evaluating and the same total number of the same color, right? So that's what you see here, that the probability of black is 1/3 always, and the probability of white is 2/3 always. Now, if you go to the different pathways, right, they're going to change. This is 1/3 times 1/3 is 1/9, 1/3 times 2/3 is 2/9, 2/3 times 1/3 is 2/9, and 2/3 times 2/3 is 4/9. And the most important thing that you want to check is, see, when you add these probabilities, they need to add up to 1. If it does not add up to 1, then there's something wrong. Okay, so this one was with replacement, and but you're going to have to do 2 that is without replacement. So you actually have an activity on page 13 on your workbook, and you also have the same thing on your homework and on your test. So without replacement, it affects what happens next. So obviously in here, you see that you have still 1 black a ball, so which is 1/3, and still 2 white balls, so it's 2/3. So the beginning does not change. What changes is the second step. See right here? So you have in the second draw, if you take the black and you do not put it back because it's without replacement, then you don't have any more blacks. So that's 0. Okay, and if you never took any white balls out because you took the black one out, then you still have both of them are 2/2. So that's equal to 1. Okay, which is different if you have taken 1 white out, then you have 1 and 1, 1 black and 1 white left. Okay, So as you see, again, when you multiply this pathway, that's going to give you 0, but this is going to give you 1/3, 1/3, 1/3. Okay. And when you add those three, you're going to get 1, right? And then on this one, let me, hold on, I think I skipped something. Let me see. No, this one, that's good. And then this. Okay. So as you see, some things are independent. They're not influenced by whatever happens in the first one. Doesn't matter what happened in the second one. And some are not. So if they're independent, like when you draw the first ball is independent from drawing the second ball, that's what we multiply the pathways. Okay. So in this one, it says if two coins are flipped and heads on the first coin, and E2, event 2 is obtaining a tail on the second coin, then event 1 and 2 are independent events because one event has not influence over the second one. Right, so this is just like the one you had on your workbook, right? So the same thing. But in some cases, you don't want to do a gigantic tree diagram. You can actually just do one of the branches specifically, especially when you have a bunch of information like this one. So you have all the letters of probability inside the bag, and you're going to take out 4 letters. But you want to specifically to know what is the probability of the first one being B, the second one being A, the third one being B, and the fourth one being Y. So you want exactly that combination. You're not interested in any other combination, just that. So we know that there's a total of 11 and it's without replacing. That means you're not putting it back. So how many B's? The first thing is count how many B's you have. You have 2 B's. So that means the probability is 2 out of 11. So if you took a B out, right, let's say we took this one out, then you're left with 10 total letters. And there's only one A, so you took that A out, so that's 110. That means you're left with 9 letters. And then the next letter you want it to be a B. There's only one B left out of the 9. And then the last one you want it to be the Y. So there's 8 letters and only one Y. And then you just need to multiply that complete pathway. So you don't have to do the whole tree diagram, just that pathway that you're interested. And then just multiply because they're all independent events. So when you multiply them, you're going to get 2 over 7,920. And when you reduce that by 2, you get 1 over 3,960. I am not going to give you anything as complicated as 6, right? If you want to go through it, that's fine, but I am not going to give you anything complicated as that. But I am going to give you the answer just in case you're curious, if you actually work it through and you're curious. So this is drawing 3, but it changes because whatever you do in the first one is going to be put in the second one. And then that changes the probability of the second one because it changes the quantity. And then whatever you take on the second one, you're going to put in the third one. And again, it's going to change it. So these are not independent events because whatever happened in the first one is affecting whatever happened in the second one and the third one. Okay. But it's just going to affect the drawing for that one. Still, this first drawing is different from this second drawing, which is different from this third drawing. It's just affecting the total number of letters in this case inside the box. Okay. Again, this is modeling without replacement. Again, so I just want to see that it's not going to, it's just very similar to what you had already. And then let me see right here. What else is important? And then these are the activities. So this is what you have on page 10 and 11 and 12, because all of that is an application problem of using matrices and using finding theoretical probability and experimental probability and doing a matrix and a tree diagram. So this is just the theoretical probabilities will be the same. So you can look at it and it will be the same. But the experimental probability, right? These experimental, obviously this is going to change depending on your results, okay? And I told you that I was going to actually, let me go ahead and write it down here. For the rock, paper, scissors, you can actually use this website. Let me give you the website. It's rpsgame.org/random. And this actually, you can play rock, paper, scissors with the computer and get some results. So rock, paper, scissors game, random. So it's pretty cool. Oops, let me see. Change color, what I want. Okay. So yeah, so you guys can use this one if you cannot play with somebody at that you live with or whatever. So okay. And then the other activity, so let me just go through again. All this is going to vary because it's experimental, and then this is the theoretical. This is going to be the same for all of you, right? So the answers are there. This is also going to be the theoretical probability. So all the answers are going to be the same for everybody. Okay. And then the last one for this section is the activity on page 13, which basically is, again, is a practice very similar to what you have on your test and on your homework, which is without replacement and with replacement. And we kind of went over that on the notes, right? So without replacement means that when you draw the second one, it's going to be affected by whatever you did on the first one. Not only the color, but also the total number of units left, right? So again, this is the answers for that activity. And over here, this is just like an additional question. They didn't ask you this, is just an additional question, like how will you read and how will you do these type of questions? Because I did put a question like that on your homework and on your test. And this is with replacing. That means you look at it and you put it back in the bag, okay? And again, you're drawing two of the squares, okay? Okay, let's go now to, so what you have on page 14 and 15 is just how to use the TI calculators. So again, I don't have instructions for all different type of calculators, but all the TIs work regularly kind of the same way. So if you have instructions for, even though it's a TI 8384, it will still work for the new one. So you can still use the same one. And then we're going to look now into simulation. So let's say in your classroom, you don't have manipulatives, but you do have calculators or computers. You can use that. We can use those to simulate. So we can use the calculators to simulate, and then we can use the tables to simulate. So those are the two simulations that you have on pages 16 through 19, which we're going to see in a minute. And then the last thing in this chapter is permutation, combinations, and counting principles, which I'm also going to show you in a minute. Okay, so this section talks about simulations using calculators, using a table of random digits. We also talk about odds and expected value. So there is no activities on expected value or odds in the workbook. So this notes should be enough for that to satisfy that part, so you can do your homework in the test. So simulation, again, is the technique of act out something. So if you don't have the resources, you don't have coins, or you don't want to mess up with the coins at school, or you don't have dice or spinners, you can actually use all of that and do simulations with a calculator or the computer, okay? So, and as a matter of fact, this table right here, this is using tables, but this table right here, let me see if this is the first one. Yeah. These tables are just like the ones that you have on your homework and on the classwork. I think it's very similar as well. The classwork, the workbook is in there. So this is problem 3. Just the first 5 rows is problem 3. And from the simulation part, and you're going to see in here that you have pick a random. So all these digits were created with a calculator or created with a computer, and they were made with random digits, okay? And they created sets of 5 random digits at a time. So you can use this table in many different ways. So for this particular, in every row, well, the total number of digits in this row, so there's 10 columns. So obviously, if we're only going to look at the first 5 rows, just like you have on your workbook, it will be 50. If you're going to assume the whole thing, then it will be 100. But we're not using all of it. So we're just using a row. And a row has 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. So in a row, you have 50 sets of 5 random digits. So in this simulation, it says you want to simulate heads and tails in a coin toss. Since we have 5 different digits in every single one of them for a total of 50, in the digits, you know that they are divided from 0 to 9, and there's 10 digits. So we understand that the simulation of heads and tails is using something that will give you half and half, right? Set up as half and half. So just like here. So in here, we selected 0, 2, 4, 6, and 8, all the even numbers to represent heads, and then all the odd numbers to represent tails. See, they have 5 and 5 each. So again, all the digits were created randomly. So for example, I'm going to select, I don't want to select the whole table. It's too much. I just selected a random row. So for example, in this one, I selected row 4 out of this square, the rectangle right here. So 1, 2, 3, 4. I selected this row right here. And then I'm looking for tails, the number of tails. And I am going to look at all the odd numbers. And that's what I did right here. And when I counted 30 out of the 50 numbers, digits are there, represent tails. So that's like 60%, which is not that bad, right? Remember, we're looking for 50, but that's good too, because again, they're random. And then I selected another one. I selected like row 2, and that one had 27. So 27 out of 50. Again, 54%. We're looking for 50% because that's what the theoretical probability of getting tails when you're tossing a coin is. This is the other activity. This is problem 4 for that simulation classwork activity. It says a baseball player has a batting average of 400,000. It said that is his probability of getting a hit on any particular time at a bat is 0.4. Estimate the probability that he will get at least one hit in his next 3 times at the bat. So let's decompact this. The reason that they have 0.4, you can look at it at like 40%, right? So 40%, that means that out of 10 digits, which goes from 0 to 9, there's 10 digits. Out of 10 digits, you have at least four of those 10 digits can represent a hit for this person, for this baseball player, okay? In this particular case, I selected 0, 1, 2, and 3 to represent a hit, okay? So, but you can have selected any other 4 numbers, either from 0 to 9, any other 4 numbers to represent a hit. Since that's the first thing. Then the second thing is we are looking for to get at least 1 hit. So he can have 1 hit, or he can have 2 hits, or he can have all 3 being hits. And as you see here, this random table doesn't have 5 digits, it has 3 digits because 3 times, right? So 3 times at a bat. So that's what they have 3, because the thing is 3 times at a bat. So again, if you see all these red ones represent a number between 0 and 3. And some of them have 1, some of them has all 3, some of them have 2, and some of them have none. And that's okay. So you're not counting the digit, you're counting how many sets of 3 have any red, right? And if you count, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 1, 2, 3, 4, 5. So that means this is a total of 50 sets of 3. And out of those 50 sets of 3, 42 of them have something red. Has either 1 digit red, or 2 digits red, or 3 digit red. So that represents 42 out of 50, which is 84%. Okay, so again, you're trying to get what percentages. So it's an 84% that when he goes to the bat, he will get a hit. Okay, so that's what it says. And then this one is another one. This one, they created a hundreds digit, and then they randomly assign 100 chocolate chips, which is a little tally, between 0 and 4. See, there's 4 here, and then there's none, or there's 1, or there's 2, or there's 3, right? So the maximum number of chocolate chips will be 4 to have in any particular cookie. And then there's 100 cookies. So 100 cookies and 100 chocolate chips. So they randomly put it in there. And then you're going to select, they want to know how many cookies has exactly 1. And again, these numbers, these tallies were assigned also randomly as well. So they selected between 0 and 4. And then that's how they fill all these blanks. So you're looking where you have exactly 1 chocolate chip in the cookie. Okay. And then when you count those, there are 34 out of 100. So as you see, we can use random digits tables that you can create ahead of time. So if you don't have calculators, you can create the random digits tables and then just pass it out to your students to use. Now, odds. Odds are not probability. Probability are parts of a whole, right? Kind of type of the thing. So you're going to look how many times an event occurs over the sample space. That's probability. Odds, on the other hand, right, it's going to be the probability that happens over the probability that does not happen. And that will be for odds in favor. Because there's 2 types of odds. Odds in favor. So let's say in favor that you win the lottery, right? So you're going to put the probability that you win the lottery, right? You have to calculate that over the probability that you do not win the lottery. And that will give you odds in favor. Odds against is the other way around. So odds against is the probability that, the odds that you do not win the lottery. So it will be the probability that you do not win over the probability that you win. So you see that it's not it is not out of any sample space because there is no sample space. Another way to view it, right, is number of favorable outcomes over number of unfavorable outcomes, right? And then odds against number of unfavorable outcomes over numbers of favorable outcomes. So I hope that kind of makes a little sense. And then here are a few examples. And we're going to do first odds in favor and then odds against. So you see the difference. So here we're rolling a number less than 5 on a die. So what are the numbers less than 5 on a die? So the numbers less than 5 on a die, it will be 1, 2, 3, and 4, right? Because we do not include 5 because it doesn't say less than or equal. It says just less than. So that means that there are 4 numbers that are less than 5. And then we have 5 and 6, right? Numbers that are greater than or equal than 5, right? So that means that there are 4 in favor and 2 against of being a number less than 5. That's what we use 4, 2. 4 that happens, 2 that do not happen, and then we simplify it as 2 to 1. Again, this is odds in favor. Then you had tossing a coin. It doesn't matter because you have 1 heads and 1 tails. So that's why this is 1 to 1, right? 1 tails, 1 heads, or 1 heads and 1 tails, right? On C, drawing an ace from an ordinary deck of cards. So you have 4 aces, right? And then 52 minus 4 is 48 not aces. Right? Not aces. So that's why we got 4 out of 48, which we simplify to 1 to 2. And you can use the columns or you can use the word 2. Okay? So yes, 4, 2, 48, or 1, 2, 12, right? So yeah, 4, 2, 48, or the columns in there. And then we have drawing a heart from an ordinary deck of 52 cards. So there are 13 hearts, and then there are 39 that are not hearts, right? So that's 13 out of 39, which is, and again, you can also write it as a fraction, 13 out of 39. The only difference is that when you're doing this, you must write both. Even if it's this one, you must write it 1 to 1 because they represent different quantities, right? This will represent heads and this represent tails. So they're different quantities. So you can write it with the word 2, you can write it as a fraction, or you can write it with a column. But they do represent different quantities. So you must write it down, both of them, okay? So all of those were in favor. Odds against, and I kind of wrote over here, the probability that does not happen over the probability that happens. So I have exactly the same 4 problems, but we're going to see it odds against. So that the number less than 5 appears. So how many are not less than 5? 2. How many are less than 5? 4. So we're going to simplify those. Okay, so as you see, it's all of these backwards. Obviously, the one that doesn't change is the tossing of the heads, because again, it doesn't matter. You have 1 heads, 1 tails. See, but this is 48 to 4. So we're going to write 12 to 1. And you must write 12 to 1. That 1 stays because it is a ratio. It's 52 that are not aces over 1 that is an ace. I mean, sorry, 12 that is not ace over 1 that is an ace. And the same thing here, drawing a heart from an ordinary deck. So these are not hearts and these are hearts. So again, it will be 3 to 1. And you still have to write 3 to 1. And you can write it with a column, as a fraction, or as with the word 2. Okay, so those are odds. And you have in favor or against. Always read what do they want so you don't make a mistake and do the other way. Now, you can also use odds because as you see right here, what happens when we add 13 plus 39? We get 52, the total. What happens when you add 1 plus 1? You get 2, right? There's 2 faces. What happens when you add 4 plus 2? You get 6. 6 is the number of faces that we have. So you see that when you add the odds in favor and the odds against, you're going to get the total number, right? To find probability as parts of a whole, right? And you need those wholes. So like this one, it says find the probability of making a totally black copy if the odds are 3 to 1 against making a black copy. So again, so you're going to have 3 to 1. So this is that it's not black over that is black. Okay, that's what this represents. And I want to know how many totally black copies, how many blacks can I have? So that means it's 1 out of 4. So you see here, if you add 3 plus 1, that's 4. So 1 out of 4 is going to be the probability, because it's parts of a whole, the probability of making a totally black copy. And that's what it says here. So if you want to find the probability, right, going backwards, then you're going to use whatever they're giving you for that part over the sum of the two ratios, right? And then the same thing will be for odds against. Whatever they give you that is not happening over the sum of the two ratios. Okay, and then we have some conditional probability. That's what they have, that line right there, the conditional probability. And it says a conditional probability is that something happens because something else already happened before that, right? So this right here, this part right here, I have another one, but this part right here says the event that B happens given that event A has occurred. So A happened first, and then B happened afterwards. And then when you have that, then you're going to have this ratio. So it's going to be always the intersection of both over whatever happened first, the probability of whatever happened first. And if you have it the other way around, that means that A happened given that B happened already. Still is the intersection, but you're going to write it over the probability of B, of whatever happened first. So for example, it says, what is the probability of rolling a 6 on a fair die if you know that the roll is an even number? So first we're going to write all the dice. The sample space is 1, 2, 3, 4, 5, 6. A is that it's an even number. So A will be 2, 4, 6. B is that you roll a 6. Okay. So the intersection of these two, basically, right, is that they have 6. And 6 is 1 out of 6 because they're 6-sided, right? And then a probability of A has 3 out of the 6, so it's 1/2. So once we calculated that, then we're going to put it in the formula because A happened first, right? So that you roll an even number first, and then that even number, one of those is going to be the 6, right? 6 is the consequence. So we're going to be 1/6 over 1/2. And then I did it down here with the division of fractions. 1/6 divided by 1/2 is same, change, flip. And then you get 2/6, which is 1/3. So that's how they got the 1/3 right there. So you can also use this formula if B happens before A happened. So just remember to divide by B if that's the case. And lastly, let me go ahead and move this because it's thinking. There we go. It's expected value. So expected value is basically the possible outcomes that you may have in an event, right? Over the probability that event happens, right? And then, so for example, let's say you're playing a game, and in that game, you can tie, or you can win, or you can lose, right? Those are the 3 options. And they're going to give you like the probability for each one of those options. And then what is the consequence of tying? Nobody gets money. Or losing, you lose $10. Or winning, you win $10, right? So what is the probability? So for each one of those. So and once you multiply all of those together, when you add all those products, you're going to get an expected value. That expected value, we can say they can be positive, it can be 0, or it can be negative. If it's positive, that means that it is a good deal that you will win, right? So if it's positive. If it's 0, that means that you have the same chances of winning, losing, or tying, which means it's a fair game. So when you have an expected value equal to 0, means that you have a fair game, okay? And if it's negative, the expected value, that means that you're probably going to lose money, right? So it's not recommended. Now, this, you have to be very careful when you're reading the problems and what they're asking you, because in some games, for example, you may have to pay first to play. In some other games, right, you play and then you lose money, and then you have to pay for it. You don't have to like pay to play. So you play, and then if you lose, then you give them money, right? So it's just like when you place bets. Oh, I bet the teacher's going to say this, or such and such is going to do this. And you say, okay, I will bet $20. So if it happens, I will pay you the $20. If it does not happen and I win, then you pay me $20. And if it's neither one of what we both expect to happen, then we both stay with our money. We don't have to pay each other, right? So in this case, it says a fair game, when pays-off are involved and the net winnings are 0, the expected value minus the cost to play a game of chance, the game is fair. So again, if you play it because you have to pay, you have to subtract that from the expected value. So let's say the expected value was +5, but you actually have to pay $5 to play, then that's a fair game because the expected value was 5 and you pay $5 to play. So you have to subtract those two. So that gives you 0. So that's just like this example. So suppose you pay, so you do have to pay in this one. You pay $5 following the game to play the following game. If 2 coins are tossed, you receive $10 if they're both heads, $5 if exactly one head, and nothing if you get tails, right? So is this a fair game? And do you have a fair winnings of 0? So probability of heads, right? So we already know the probability of tossing 2 coins, right? Because we did the first experiment. So heads will be 1/4. And then head tails or head tails head, that's 1/4 plus 1/4, which is 2/4, which is equal to 1/2. And the probability of tails, which will be 1/4. So now we're going to calculate the expected value. That you get 2 heads, you win $10. So 10 times 1/4 is 10/4. If you get 1 head, you mean $5. So that's 5 times 1/2, which is 5/2. And then if you get tails, that's 0. You don't win anything. So the expected value here is $5. But remember that how much do you pay to play? You pay $5 to play. So when you subtract $5 from the expected value minus the $5 that you invested in playing, that gives you the $0, which means it's a fair game. Okay, so hopefully that makes sense. I think the one on your homework, you don't have to pay to play, but you lose money. So that means you will subtract it as part of your expected value. Okay. Okay. Let me move on. Give me 1 second. And then the next one, basically, these are the activities that you have that is related to using a calculator with random integers. And I explain here how to use each one in that activity. You can also generate random integers using this website. So you're welcome to use that one too. If you don't have a graphic calculator, you can use that. And then I did also with a spinner. You also have a random integer there. Okay, so the last one, the last part of this chapter talks about fundamental counting principle, permutations, and combinations, okay? So fundamental counting principle, and you probably heard this before in 1350, right? Is the different ways in which you can, different type of arrangements that you can get, different scenarios, right? So let's say you're going to Vegas for the weekend or to the beach for the weekend, and you plan on taking 3 shirts and 2 shorts, 2 pants, right? So how many outfits do you have, assuming that you can, everything combines? So you're going to have 3 shirts times 2 pants, and that is 3 times 2, which is 6. And you can also see this, remember those tree diagrams over there for probability? You can also see it that way. So you have, this is a menu on a restaurant. You have 3 types of burgers, that's the 3. You have 2 types of sides, fries and salad, that's 2. And you have 2 options for drink, cola and juice, see? And then you will have a total of 12 different possible arrangements. See, 2, 4, 6, 8, 10, 12. So 12 possible arrangements. So you can see it visually with the tree diagram, but you can also just multiply because that's what counting principle is, okay? Multiply all the possible arrangements. And then the other ones is about permutation and combination. Now, what is permutation? Permutation is the arrangements when order is important. So no repetitions is allowed. So think about it. If you have 3 letters, right? And how many ways can the first letter come, right? Out of the 3. Well, you have 3 options for the first letter. We got 3 options for the first letter. Let's say I selected the A first. Then how many options do you have for the second letter? 2. Let's say I selected the R. And how many options are for the last letter? 1. So if I want to find the arrangements, basically I would just multiply 3 times 2 times 1. And that will give me the arrangements for 3 letters, and I can find all the different arrangements where the order is important, right? So the order is important on who comes first. And then look how different. Here we got 6 with 3 letters. Just to adding 1 more letter, look how many more arrangements we have. Because now we have 4 possibilities for the first one, 3 possibility for the second one, 2 possibility for the third one, and 1 possibility for the fourth one. And then 4 times 3 times 2 times 1, that's 24. And the fun fact about this one specifically is that this type of arrangement, when you multiply by the previous number on a number line, if you want to think of that way. So I had 4 letters, so it's 4 times 3 times 2 times 1. Well, I had 3 letters and 3 times 2 times 1. So you see how you're going down? That arrangement and algorithm is called n factorial. That's how you read this. N factorial. And n factorial says exactly that. So whatever number you have here with the exclamation point means that you're going to start on that number and then you're going to decrease it by 1 all the way until you reach 1, and you're multiplying. It's not addition, it's multiplication. Okay. And then there's some, we're going to see the application later on, but there's some definitions. So for example, 1 factorial is 1 and serial factorial is also 1. Okay. That's the definition. For example, in this one, it says find the number of ways of choosing 3 initials from the alphabet if none of the letters can repeat. Again, permutation, none of the letters can repeat. So, and I need 3 letters. So how many options I have for the first letter? If we're talking about the English alphabet, we got 26 letters, right? So that means I have 26 options for the first one, 25 options for the second one, and 24 options for the third one. So that gives you a total of 15,600 different ways that I can assume 3 letters from the alphabet. I'm sorry, this is keep moving. Okay. Why is keep moving this? And we are going to, this is the formula that you're going to have to use. This one right here. This is the formula that you need to use. Write it down, because that's the one you're going to be using for the workbook. That's the one you're going to be using for the homework. This is the one that you're going to be using for the test. So this is the official formula for permutation. Right? And you want to be able to know how to use this, because you don't want to, let's say you're selecting out of 300 people, you're selecting 150. You're not going to write the previous way, right? So we got to find something, a resource. And I am going to require some minimum work for this part and for combinations too, that you have to show before you can use your calculators, okay? So yes, so probability in the calculators and the TI, I think is math. And then you need to use the little arrow to move to the right for probability. And then I think the probability is 4. So, and then you will enter the N and you will enter the R, where N is the total number of sets or elements in the set. So let's say out of 30 songs that you have on Spotify, you want to listen, you want to put 5 of those in a separate, I don't know, folder, whatever. So playlist. So 30, select 5. So R will be 5. And then you will do n factorial minus n minus r factorial. The factorial goes after you do the subtraction. Okay, so let's say that I want to do that same problem. I want to do it with the formula instead, right? Then I would do from 26, select 3. So 26 factorial over 26 minus 3 factorial. That's 23 factorial. And if you see, I did not write everything out, 26 times 25 times 24 times 20, and continue, because I know that this can cancel with that. I can cancel that. And then I'm left with 26 and 25 times 24, which is a 15,600. Okay, so that is possible. Now there is another type of permutation, which involves when some elements are repeated. Some members of the set are repeated. And for that one, you would not use the previous formula. We would not use this one. You're going to use this one. And what is this one? So let's say that you're trying to use, see, I have here bubble statistics, Mississippi, right? Letters that repeat. So for example, bubbles, I want to pull 1 letter out. So that means that I have 3 B's, right? The U and the L and the E don't repeat, so I don't have to worry about that. So I'm going to take the total number of letters, which is 6 factorial, over 3 factorial. And that's going to give me 120 different combinations. Look at statistics. Statistics has, what, 3 S's, 3 T's, 2 I's. And it's not writing. Hold on. 2 I's. So I would do 3 factorial for the S, 3 factorial for the T, 2 factorial for the I. And then on this one, yes, you may, if you were doing it by hand, you may want to expand it because there's more cancellations. See, I can cancel 3, 2, 1 with this 3, 2, 1. But you're still left with 3 times 2, which is 6. So I can cancel with that 6. And then you're left with this 2, which I'm going to cancel with this 4. And I'm going to write a 2 on the top. And now everything in the bottom is 1. So I just need to multiply the top. 5 times 2 is 10. Times 10 is 100. And then 9 times 8 times 7 is 504. So you add 2 zeros because you're multiplying by 100. See? So yeah, so you're able to expand when you have more than one repeating thing. So you want to be able to be careful with those. And then combinations, they're going to look very similar to permutation, but in the combination, remember that word cars that we had 6 different ways? So now I don't need 6 different ways because the prize only goes to one person in the family. So even though all 6 of you compete, only one can be the winner. So I don't want to repeat the same people. So the combination in this case, the order makes no difference. So that means you need to assume that when you have the same type of people, we don't want that. So what are we going to do? We are going to see this part right here, and this is permutation. So the only difference that makes a combination is that we added that division of R factorial. Still N represents the total number of elements. Still R represent the number that you're going to be selecting. So for example, it says, how many combinations are there if 3 out of 5 are winners when you have A, B, C, D, E? So if you have A, B, C as your winners, you want to eliminate BCA, ACB, BAC, CAB, and CBA. Why? Because it's the same 3 people in different order. So the order is not important. So I want to be able to eliminate it so I don't repeat the same 3 people, right? It's just that you're having a party between you and your friends and you and your partner, and then your partner send invitation and you send invitation, but you don't want to send invitation twice if you guys share common friends, right? So that's what we want. We want to avoid having the same people, right? The same unit, the same members. And that's what we divide by that R factorial. So out of 5 letters, you're going to select 10. Select 3, sorry. So you do 5 factorial, 5 minus 3 factorial, divided by 3 factorial. So 5 minus 3 is 2 factorial, which is 2 times 1. And then I'm going to expand the 5 into 5 times 4 times 3 factorial. This cancels. This cancels with a 4. And you end with 5 times 2, which is 10. So there are 10 different combinations when you have 5 letters and you want to select 3. The Library of Science Book Club offers 3 free books from a list of 42. If you circle 3 choices out of 42, how many possible choices are there? Again, out of 42, you select 3, doesn't matter the order. So you don't want to repeat the same combinations of 3s, right? So again, once you divide 42 minus 3 factorial is 39 factorial. And then I expanded the top all the way to 39, cancel the 39. And then I did the 3 times 2, which is 6. And I cancel it with a 42 and I got 7. And then I did 7 times 41 times 40, which is 11,480, right? And the same thing with this problem, okay? Now, in occasions, some of your combination problems, and you do have some in the workbook, and you also have some in the homework as well and on the test, may require you to use also counting principle along with a combination. So let's say in the class of 12 girls and 10 boys, you want to form a committee of 5 people. That right there, right? That right there is a combination problem. But this is the thing. You specifically want 3 girls out of the 12 that you have, and you want 2 boys out of the 10 that you have. So now you have to do the combination for boys and the combination for girls, and then multiply them, right? You have to use the counting principle. You multiply those 2, and then you're going to get the total number of committees with 3 girls and 2 boys, okay? Now, the number of combinations, if they ask you what is the probability, which is what I asked you in part B, you need to find how many total combinations of 5 people out of 26 can be formed. And that's what 22 out of 5 is. You're finding the total number of people, total number of combinations possible if you select 5 people out of 22. And then now that you have the parts and you have the whole, this is the part over the whole, and then you simplify it and it's around 38%. Okay. Okay. Then we have, again, in occasion you may see that you have no boys or no girls, and you have a 0 factorial. Remember that 0 factorial is 1. And then this is the other part, the last activity that you have in your workbook. And again, it's all in here, all the answers. The same answers you're going to find under the activity roster, activity links. I put in there answers for all activities. So, and I recall the formula, and I work them out, and then also the permutation formula, and I work them out. So at this point, you can always put it, this is the minimum work required for the homework and for the test. You need to set up the formula, regardless if it's permutation or combination or counting principle. And then once you have it set up, then you can put it in the calculator and find the answer. But otherwise, you need the minimum work. Okay. And I think that's it. That's it for this chapter. No, we're better. Okay. So as you see on this homework one, this is for chapter, the first chapter, right? Or the class notes chapter 9. This is all about probability statistics. And I want you to remember probability is out of the total, okay? That's what they're talking about. So for example, if you're reading this, it says flank steak with low fat content. So you're gonna go to flank steak and then low fat content. So that is what? 433 people. But when they talk about probability, it's out of the total. The total was 1,050. So you see that that's how you find, and then you divide, and like it says here, round to 4 decimal places if needed, and that's how you're going to write it down, okay? Remember, probability is always going to be between 0 and 1. It's never over 1. Now, here it says rump roast or flank steak. If you guys remember your sets from 13 to 15, or means union. So that means you're going to find what are the rump roast with high fat content, right? Rump roast. And what is the flank steak with high fat content? So it will be like the addition of these two, which is down here, over the total, right? So the total will be 1,050 again. And then again, you round to 4 decimal places. And then again, these are scenarios. These type of scenarios are the ones you are going to have on your TEA exam. So you want to be able to start getting used to when you see these in the homework. So you want to be able to get used to those, because those are the type of questions that they're going to ask you, more scenarios wise, and how do you use this and how do you do that. So it says a teacher has each of his kindergarten students flip a coin 20 times while keeping track on which side the coin lands up, heads or tails. This is an example, an activity that will help the student develop a beginning understanding of, well, what are we talking about here? Are we talking about patterns and functions? Are we talking about real numbers and loaf operations? Are we talking about fractions, cents, and parts of a whole? We're talking about what? Data collection, right? How to collect the data and then get probability. And then you are going to have exactly the same thing, not with these 3 toss fair, but exactly the same thing on your test. You're going to have to tell me what is one outcome given this experiment. So not necessarily in this case is 3 coins, right? But in the test, I can give you any other experiment. So, and then you need to write one outcome. You need to write an event. Outcomes and events are not the same thing. So for example, on that chapter 9, you had a first chapter, you had a lot of activities that you play with a partner, right? To see if you win or lose, okay? So an event for some of those were that if you got matching, when you were tossing 2 coins, player 1 got a point if the 2 coins were matching. That means if they got heads, or tails, tails. That is a specific event, if the coins are matching, okay? And then you can put as an outcome, it can be heads, tails, tails, okay? But here is 3 coins. So if you're going to put something like that, you needed to put heads, or tails, tails, right? Or you're only looking when you have 2 heads. That's a different story, right? So you can have heads, tails, head, tails, head, tails, head, tails, head, right? So you can have all the different combinations for when you have 2 heads. Or you can say when you toss a head on the last coin. So again, the events are very specific. So you come up with that event. And then the sample space is a collection of all outcomes. Okay, so all the outcomes. And then you need to write all the possible outcomes when you toss 3 coins. This is also coming on the test. You need to create your own. Then you got a probability of 1 and a probability of 0. You need to tell me an event that gives you a probability of 1. And I always tell my students, don't make it complicated. Make it as easy as possible. So don't use coins, don't use dice, don't use spinners. Do as simple as a box of crayons or a box of markers. You have a whole box of red markers. What is the probability of getting a red marker? 1. See, and that's an event. Having a box of red markers and the probability of getting a red marker out of the box. That's 1. Same red box. What you have a box of red marker? What is the probability of getting a blue one? 0, because there's no blue one in the box. So that is for sure a 0. So when you make it complicated and try to use coins that the students or dice, they messed up because those are not prone for getting a probability of 1. Okay. And then again, these are, I kind of went over this last class, but with replacement, without replacement. So you need to make sure that that you go over specifically, and you have activities in the workbook like that was with replacement and without replacement, because it does leave a tree diagram that is different, and you have one of those on the test as well.
And then when they ask you for probability specific, you need to follow the tree. Okay, so you need to follow that tree. Let me see here. And then you multiply the tree branches, but you add the different ones. So for example, this is find the probability of at least one blue marble is drawn. So you're gonna find out all the combinations that have at least one blue marble or two blue marbles, and you're gonna add all those probabilities individually. Odds is not this, and this is one that the students always get wrong on the test. Odds are not probability. Like, it's not out of the whole. So odds against, that means the probability that happens over the probability that does not happen. So, sorry, odds against, probability that does not happen over probability that happens. So again, you want to be able to have, if they're talking about even numbers and odd numbers, right? So if there's not even, it's odd. You're going to find how many even numbers you have in the bag, how many odd numbers you have in the bag. And then it says odds against, that is an even number. So that means you're going to do the probability will be, or the odds will be, the probability that is not even over the probability that is even. So how many outcomes are not even over the number of outcomes that are even. So, and then reduced format. So from 1 through 15, you actually have what? You have 7 even, right? 2, 4, 6, 8, 10, 12, 14. So there's 7 even. So that means the other remaining marbles or whatever, or bag, they are odds. So that means this right here, odds against, will be 8 over 7. Because there's 8 that are not even, over 7 they're even, because it's odds against. If this changes and then do odds in favor, then it will be 7 over 8. So you see that what one little word changes how you write the ratio. So if it's odds against, is the probability that happens over the probability that happens. And if it's odd in favor, it's probability that happens over probability that does not happen. So again, but it's never over the total. Now, if you're asking what is the probability of getting a ball that is an even number, then that is going to be what, 7 out of 15, because there's 15 in the thing, because probability is parts of a total. So I hope that makes sense in there, because this is one that always the students get wrong, not only on the homework, but also on the test. You also have a random table to be able to use to find whatever simulation they're asking you to find. And then again, if they're telling you that there's 50 tosses and they're tossing 5 coins, right? So you see you have 1, 2, 3, 4, 5. There's 5 coins in every set right there. And you got 50 of those. So again, you want to be able to highlight and use a highlighter on when you have exactly 2 heads. And they're telling you that a head is from 0 to 4. So any set that has 2 0 to 4 numbers, exactly 2. So no more than 2, no less than 2. So for example, this one will not work because you got 0, 4, and 3. That one has 3. That does not work. It has to be exactly 2. So exactly 2 will be what? Let me see. The first one will be exactly 2 because it only has what? 1 and 2, and the rest are bigger than 4. So see, that is one of them. So that's what you're gonna do. You're gonna go through all 50, and then you're going to highlight the one that has exactly 2 of the 0 to 4. And then you're asking for probability, so it's gonna be part of the total. So let's say you have 15, that will be 15 over 50, and then you're going to simplify that fraction because it's always need to be in a simplified fraction. Now again, 15 is not the answer. I'm just making something up here. And then again, this is just like the activity that you have on the very end of the first chapter, that it tells you about permutation, combination, and counting principle. Permutation and combinations is out of a total amount that you have, you're going to select a field. So let's say you have 10 runners, and you're going to award the same prize to the first 3. So out of the 10, I'm going to select 3, and they're all going to be getting the same thing. That is a combination problem because the order is not important. But if you had 10 runners and you're going to assign different amount of money to the first, second, and third, then that is a permutation. It's a different formula. So because the first one gets gold, the second one gets silver, and the third one gets bronze, and don't get the same amount of money either. So that's a different story. That's a permutation. Okay. And then counting principle is basically when you're talking about finding all possible arrangements. So if you have you're buying a car and you can decide between the type of car and then the color of the car, right? And the rims of the car. Those are 3 different things. And let's say the color of the car, there's 9 colors, and the type of the car, there's 2 types. And then the rims of the car, there's 3 types. So you're going to multiply 9 times 2 times 3, and that's going to give you the total different arrangements that you can come up with given that information of the type of car, the color, and the rims. So again, it is important that you know which one is what, because I am not going to tell you this is a permutation problem, this is a combination problem, or this is a counting principle problem. You need to be able to recognize them and use the appropriate formulas. And no, you're not going to have the formula. So you need to be able to know what the formula is, and then you can use a calculator. Once you have set up the formula, then you can use a calculator and solve it. But you need to be able to write the formula, plug in the numbers, and then you can use a calculator to find the final answer. But otherwise, you can't. And you have a whole section in your workbook on how to use, how to find permutation, combinations, and counting principles. So I give you that information on the workbook on page, 14, 15, and then, 14, 15. I gave you those. So there's a lot of information in there. You're just going to find out the permutation and combination one. Okay. And then basically the other ones here in 10, they're just scenarios. So, so you need to, and then odds. So is it a fair game? So, and then you got to be able to read, when they find odds and do you want them, they're asking you different things. They're asking you, do you want to play? Is it a fair game? And explain and show your work to prove your answer. So it's a fair game when the amount of winning and the amount you're investing is equal, it's the same. So when you add those two, you should get 0 as your answer. That is when you determine if it's a fair game. But if you add how much you invest and you add how much you lose, and it's negative, that means you're losing. It's not a fair game. And if you add the amount you invest and the amount you lose, and you get a positive number, that means you're winning. The odds of you winning is positive. So obviously, if you want to play, if the amount is positive, but if the amount is negative, you do not want to play. And either one, if it's positive or negative, it's not a fair game because it's not equal to 0. So to be a fair game, the amount of winning plus amount of losing has to be equal to 0. And if it's not, that is not a fair game. Now, do you want to play? Well, of course, is it positive? But yes, you want to play. If it is negative, the result, then you do not want to play because you're losing money. And that is what you want to do. So you will find you're going to show your work, right? So the expected value will be the expected to win and how many cards you have and how much you win for. You multiply those two. And then if you lose, also remember to subtract if you lose, or you can just add a negative there and then negative. And then when you're adding all the different ones, you're going to subtract because it's negative. So, and then, and again, if the final answer is 0, then it's a fair game. If you want to play or not, well, it's up to you if it's 0, if it's a fair game. But if you're winning, like if you get a positive, then yes, you want to play because there are chances that you win. If it's negative, no, you do not want to win because you're going to lose money, right? So, and if it's 0, then it's a fair game. So it's up to you if you want to play or not. So, but you want to be able to show your work to prove your answers for these two right here. And then 10, again, there are 3 student scenarios that you may want to choose from according to the definitions that we talked about in the chapter, according to, the multiple probabilities and such that they have in there. Okay. So, and then it's not selecting one, you have 3 different scenarios. So you have to have 3 different answers. Okay. Which you have to choose which one is the correct one for event 1, which is the correct one for event 2, and which is the correct one for event 3. So there should be 3 different answers for each one. Okay. So for number 10, because there's 3 different scenarios.